So I get a lot of questions about cohesive sediment modeling in HEC-RAS. We have a cohesive parameter editor where you can go in and add parameters like the critical shear stress and the erodibility. And we leave those blank by default because we don't actually want anyone like pushing buttons without having some idea of what those properties are. But the question is, how do you get those numbers? And in our agency, when you want to get those numbers, I send you to the team that I had on the podcast in this episode. We had the Corps' Cohesive Sediment Brain Trust, is what I call them, from ERDIC on the podcast. David Perkey, Jarell Smith, and Danielle Tarpley. And I asked them this question. I asked them, how do you get these cohesive sediment parameters? And they explained the SEDFlume and how they use the SEDFlume to get these parameters. And we cut it with some footage so that you can see the kind of work that needs to be done to get cohesive sediment transport parameters for the excess shear equation in HEC-RAS and other models.
Yeah, so if you were modeling sand transport, you could stop there at just the size description. But we've got to go a little farther. All we've done with the size description is to say what this material is made of. Because of the complexities that we've discussed, we have to more or less empirically know the rate at which the bed will erode.
There's just too many different physical processes going on.
Too many unknowns.
Yeah.
I won't say that we'll never get to a physics-based erosion, but I doubt that I will see it.
Yeah.
So we're left with making measurements, and we know that erosion is related to shear stress. We suspect that it's related to density, but there's other complicated factors. So we usually just have an equation with bed shear stress and maybe density, and 2 or 3 empirical factors.
And how do you determine those empirical factors?
Yeah, so that is done the way everyone does it. You would make measurements and relate your measurements to this form of equation that you have assumed that the material behaves like. And if your experiments follow those expressions, then you have some confidence that you're describing it adequately for this set of sediment. Now, if you brought me a different sediment, then I have to do the testing again and come up with a different set of factors. And that's just the state of the science presently.
All right. So can you describe this experiment that we're doing?
So, for a specific theory, what we have is an adaptation of what we call the SEDFlume.
Okay.
SED actually doesn't stand for sediment.
It doesn't.
Sediment is part of it. Sediment is the S,
Okay.
right? But it's the sediment erosion with depth, SED, flume. It's a small flume that is able to accept a core.
Yeah.
That can be a core that we've collected out in the field and we're eroding, or a slurry material that we made up in the lab.
And so this is like a Shelby tube.
4-inch diameter tube.
Yeah.
Yeah.
A cylinder.
Yeah.
A cylinder of mud in situ.
Yes, a cylinder of mud with a plunger on the bottom of it that essentially we have a piston, a screw jack, that we extrude the sediment up into the flume and keep the surface of that sediment surface essentially flush with the bottom of the flume. And then we introduce flow, of course, through the flume, and are measuring the flow rate, and through that, what the applied shear stress is to that sediment surface. And at different shear stresses, we're monitoring and recording when erosion starts that we can see visually with our eye. So maybe not first incipient motion of the first particle, because we're not able to, as humans, we're not able to resolve that.
50 microns.
Right, yeah. And so what we term like our critical shear stress is what we can observe as it's a functional critical shear stress, right? And then of course ramping up that applied shear stress or flow rate, we see how does that erosion rate change under different conditions, which then of course allows us to generate a curve to allow us to predict what erosion rate occurs at different shear stresses and kind of back through that. What would if you wanted define your critical shear stress as X value, well, what shear stress would be needed to do that? And then as we move through the core, as we were talking about with consolidation and compaction and density increasing, we might anticipate that behavior to change. And so hence with depth, so as the more we extrude, we're also able to see is like if at the very surface I'm getting conditions, 1 or 2 centimeters within the core that look like this, but at a depth of 10 or 12 centimeters, I've noticed that my erosion rate has gone down and I'm needing to apply more shear stress and more flow to get the same behavior. So it allows us to track that and measure it. So that those parameters, we can kind of develop a curve and come up with our empirical, formula to say this is what we think for this material and allow that to be incorporated into the model.
So I don't see these much anymore, but when I was a kid, if the ice cream truck came by, you could get a thing called a push pop.
Yes.
And it's like ice cream and it had a stick. The ice cream is in a cylinder and it's surrounded by cardboard and it has a stick and you'd have to let it melt a little bit, but eventually you would push the ice cream up through the cylinder. And basically what's going on here is you're kind of trying to lick the ice cream to keep it flush and push it up and kind of measure that rate, except it's all much more technical.
Where do you think the SEDFlume idea came from?
And so you're measuring two things. You're measuring this critical shear stress when things start to move. But you're also, as your shear stress increases, you're measuring how the erosion rate increases with that change. And then you're also looking at how that changes potentially vertically in the core.
Correct. Yep.